Good afternoon, everybody. Welcome to Wednesday Organic Chemistry 2. And we're going to switch over and look at Chapter 19. That's Chapter 19. Sorry, it's not even Chapter 18. Something's wrong here. That's old. This is new. It's 18. Carboxylic acid derivatives. You'd think I'd know my own chapters by now. We have review reactions that created carboxylic acid derivatives in the first box. We looked recently at diazomethane creating methyl esters. Remember, it was limited to methyl esters. Very fast reaction, but very limited utility. We can make more generic esters using the classic Fischer esterification, a condensation reaction involving a carboxylic acid and an alcohol, where the carboxylic acid loses OH and the alcohol loses H, and we create water as we create a bigger molecule called an ester. We did the mechanism and everything. And we've also looked at very recently the reaction of carboxylic acids with thionyl chloride and pyridine to produce acid halides. These are all carboxylic acid derivatives. Methyl esters, other esters, and acid halides. So you might be getting an idea that you think you know what a carboxylic acid derivative is. You're thinking it has to have a carbonyl. You would be partially correct, but also incorrect when we see a carboxylic acid derivative that does not even have a carbonyl. We'll get to what a real carboxylic acid derivative is shortly. A main focus reaction in this chapter is called Nucleophilic Acl Substitution. You can give it the more generic name acylation. Both of those present a problem if we don't know what acyl is. Acyl groups are carbonyls attached to something. The R has to be C or H. And all of these have the same acyl group. So when you transfer a carbonyl attached to an R to something such as a nucleophile, we say the nucleophile was acylated. So we substituted the nucleophile for the leaving group. And leaving group short form is right here. In the first two examples, these are both good leaving groups. The first example is an excellent leaving group. So quick review of excellent leaving groups. The conjugate base of a strong acid. And we have good Lg, conjugate base of a moderate acid. We'll give that a stricter definition, but it's a guideline, not a rule. So if the acid has a pKa greater than 0 and less than 11, let's say 12, somewhere between 0 and 12, then its conjugate base is a good leaving group. So here we see Cl minus, the conjugate base of HCl, which has a pKa of -5, making this in the excellent leaving group category. Here we have a carboxylate leaving group, which puts it in the good leaving group category because the carboxylate is the conjugate base of a carboxylic acid with a pKa of 5. That's in this range here. greater than 0, less than 12. Carboxylic esters do not have a good leaving group. This is a poor leaving group. And this one is extremely poor. RO minus is the conjugate base of an alcohol. Alcohols have pKa's at 17 and 18, somewhere in that range, and that is above 12. This is the conjugate base of an amine, and an amine has a pKa of 40, and this is extremely poor. You're going to need very harsh conditions to do these kinds of reactions. You don't need harsh conditions at all to do the ones at the top. This whole chapter is organized based on reactivity, so we will focus our studies first on acid halides, the most reactive carboxylic acid derivative in the chapter. And we will work our way down to the least reactive here. And we will also look at nitriles, which do not have a carbonyl, and imides, which have a nitrogen with 2 carbonyls. If you want an example of an imide there, look at thalidomide. That was an imide. Nitriles are found in many medicines. All these functional groups are useful either for synthesis purposes or their own functional group is necessary for drug activity or functionality for organic molecules. Back to our original question, what makes all of these carboxylic acid derivatives? You can no longer say they have R attached to a carbonyl because of nitriles fitting in the same category here. I'm going to cut to the chase. Every one of the acid derivatives, carboxylic acid derivatives, all 4 of these, and this 5th one, and this 6th one, all have a carbon with 3 bonds to more electronegative atom or atoms. So carbonyl with bonds to 2 bonds to O and bond to Cl, that's 3. Carbonyl O, carbonyl O, carbonyl N. Carbon with 3 bonds to a more electronegative nitrogen. So everything here has a carbon with 3 bonds to a more electronegative atom. And an even stricter definition of a carboxylic acid derivative is related to a reaction we're going to see shortly, and that is upon hydrolysis, that is using water to break down the acid derivative. Every time you do a hydrolysis reaction of a derivative, you get the original carboxylic acid that the molecule was derived from. So we will, by the end of today, be able to do a hydrolysis mechanism for every single one on this page, all 6 of them, and you will end up with carboxylic acids every time. And naming. Naming is going to be a pretty big chunk here, so I don't want to cut a segment this short. So we'll probably do naming of our first 2 derivatives and then end our segment. And then pick it up with more naming. When you're naming a derivative, you always need to think of the original acid and its name. So let's look at the names. In chapter 17, we learned how to name this as acetic acid or ethanoic acid. And look at what happened to that name when we made it into an acid halide. Everything here is acid halides. Even down here, when it's not a carboxylic acid, they're still acid halides. You lose the ic acid, so that will be gone, replaced with ill chloride in this case, ill halide in generic case. That even works with ethanoic acid. You lose the ic acid and you keep the O and you get ethanoyl chloride. Sounds awkward, but it follows the exact same pattern. Benzoic acid, when it has a halide there instead, becomes benzoyl bromide. You've probably heard the name benzoyl before. Some people more than others. including myself. This is a benzoyl, and it can be attached to things other than halides, like a peroxide. And I'm getting flashbacks to my adolescence right now. This is called benzoyl peroxide. And as a medicine, it works as all peroxides do, as a disinfectant. Why can you not use hydrogen peroxide when you want to use benzoyl peroxide? Well, if you don't know already, benzoyl peroxide is an acne treatment. To disinfect an acne blemish, you need to penetrate through oil. This is a solubility issue. This molecule's not very polar. It will dissolve in oil and then penetrate deep into the sebaceous gland and do its disinfecting. Hydrogen peroxide would do the job if it got there, but it stays on the outside because it can't penetrate through the oil. There you go. Nothing to do with nomenclature, but some interesting stuff. Let's see, benzene carboxylic acid is the alternate name for benzoic acid. So if you want to use that name, one, you'd be in a rare company. Even organic chemists almost never use that name, but it follows the same rule. Benzene carboxyl bromide would be the name. And if you'll notice, this one doesn't exactly follow the rule. We're supposed to lose the ic acid and put ill bromide, but that would add a second ill. It would be carboxyl ill. So I would be fine with that if you did that on a test. You're following these rules exactly. But the people at UPAC thinks that sounds too awkward, so they dropped one of the YLs. And here we have E-pent-3-enoic acid. Follow the same rules. And you get E-pent-3-ene oil fluoride. Our old friend paratoluene sulfonic acid. There's TSCl, one of its short forms, PTSCl, if you want to be with more information, or CLTS to have it backwards. And it follows the same rule. The ic acid is now an acid halide, so it's an ill chloride. And phosphoric acid can be made into phosphoryl bromide. Some chemists will say phosphoryl tribromide. There's nothing wrong with that whatsoever. Their argument is you could have replaced 1, 2, or 3 of the OHs with BRs. That's a fine name. And naming acid halides isn't too bad. Naming anhydrides, I think, is even a little easier. It's reminiscent of naming ethers, which was also reminiscent of the common naming for ketones. You name the two pieces that make the anhydride, and then you throw the word anhydride at the end. So with symmetric anhydrides, like the first three, the first three are symmetric. You'll only see one name before the word anhydride. That implies you use 2 acetic acids. If you're doing some bookkeeping, you're going to need, in synthesis, you would use 2 of these, and you'd condense them, and you'd make 1 acetic anhydride and water. That's why they're called anhydrides. You brought 2 acids together to make an anhydride, and there's the water that you lost. It's 2 acetic acids without their water. That's what it says, acetic acid without water. And ethanoic acid without water. Here you keep the ic. Logical, since you kept the O between the carbonyls. So it still has the ic, and it's now acetic anhydride. Benzoic becomes benzoic anhydride. You can use the UPAC names, follows the same pattern. Same story for the third one. And when you mix two different acids to make an anhydride, what's the story there? Well, you list alphabetically the two acids that were used, two separate words. So isohexanoic is this one. We'll do the alternate name too. That would be 4-methyl pentanoic acid. Pentanoic acid. And M would still come before P. So you got 4-methyl pentanoic. And the other acid was iso. No, that was iso. Then the other one was pentanoic acid. And now they are together in what functional group? An anhydride. So we have that word at the end. Now, sometimes we make anhydrides like these, where there's two things together to make this, and that's chromic acid, and it becomes chromic anhydride, and you're more familiar with its conjugate base. You could treat that with low concentration of potassium hydroxide, and you get one of your polyatomic ions from back in the day, and one of our ions used to make chromic acid. That's dichromate, isn't it? And we know now is an anhydride. It's an anhydride, and it's also the conjugate base of chromic anhydride. There you go. And phosphoric acid can be condensed to make phosphoric anhydride, but your biology instructor won't call it that. They'll call it diphosphoric acid, but more likely they'll call it, we'll buffer to pH equals 7.4. I need to point out that 7.4 is above all four of the pKa's here. You don't have to know the numbers, but realize 7.4 is a higher number than all four of them, so it's more basic than those acids. So every single one of them gets deprotonated, and you are responsible for two names of this very common biochemical anion. Some of you already know this name, diphosphate. Now you know a little more information that it's an anhydride. Oh, doing some funky stuff here. There we go. But later on, you're going to get some biochemistry teachers that prefer calling it pyrophosphate. I don't know why I can't get rid of that. Maybe I can move it and then get rid of it. Pyrophosphate implies that it was made using heat. A pyromaniac is somebody who loves fire. So pyrophosphate is another name for diphosphate. You need to know that. And this brings to a conclusion our first segment. We will continue with nomenclature, always going back to our guide right from the beginning here. We're going to continue with carboxylic esters and how to name those, and then amides, and might as well try to finish all three of those in our next segment, where we conclude nomenclature of carboxylic acid derivatives. So I'll see you shortly.